The title is The Role of Distributed Generation of a Hydrogen Society. And it addresses one of the areas between the electric vehicle and the electric grid, where we're seeing this merging confluence between the two. Part of that is giving rise to the concept of dual fuel vehicles, as we've heard described. That's giving rise to smart grid technology in order to manage at least the electric charging aspect of it. Another perturbation on the electric grid that is somewhat associated with recharging vehicles would be solar and wind renewables. And that's giving rise to this question of intermittency and its impact on destabilizing the grid. Part of this future is, in fact, distributed generation. And in that future, we have both electric charging and hydrogen refueling. So what I've been asked to do is take from that list distributed generation and hydrogen and provide you a bit of a snippet on what role distributed generation is going to play in this hydrogen future. What that begs is, what is distributed generation? Most of us are aware of that, but just as a reminder, we have central generation with a variety of resources to give rise to electricity on the grid. And what we're seeing is a population over here at the point of use of various power generation technologies. Here, solar. We also have the evolution of gas turbines or microturbine generators and smaller applications. All of this is under the rubric of distributed generation. We're now seeing other technologies come about, particularly to handle this perturbation of electric charging and intermittency of renewables, and that's electric battery storage, just in the area of its infancy in being considered and deployed into the electrical grid. And we call those distributed energy resources. What is distributed generation then? This is the area of application, and this is a glossary which you can read clearly from the Governor Schwarzenegger's California Highway Blueprint. You can see a lot of different items here that are being defined, but over here you see distributed generation, and if you blow it up, it basically says that distributed generation is the provision of electricity and a thermal product at the point of its use up to and around 50 megawatts of generation. So we come back to our map, we see solar and microturbine generators populating this space, but we're also now seeing the emergence of another technology right here, for example, and that's the stationary fuel cell. So let's talk a little bit about the stationary fuel cell. Among its attributes would be a high fuel to electrical conversion efficiency. Right now, with the advanced stationary fuel cells, that's 50% and going north rapidly. It's also a technology with a high quality heat product for good thermal capture. It is acoustically benign, meaning it's quiet. And it's virtually zero emission of criteria pollutants, some pretty remarkable attributes, if you will. And then it turns out to be a fortuitous fit right now in what is being demanded in the community. For example, distributed generation, it's a nice fit. For example, a good partner for the Renewable Portfolio Standard, RPS, in order to kind of buffer this intermittency that I alluded to. And then it itself, if operated on a renewable gas, is a 24/7 generator of renewable electricity. It's a very fine technology to be evolving to handle the California directive under AB 32, the mini Kyoto for California. And the market is starting to see the attributes and beginning to cry out for the technology to be deployed. Now we're focusing here on distributed generation, so in that spirit, let's just talk a moment about why distributed generation is garnering popularity. The first word you see here is local control of the customer, of not only relying upon the grid, but having another resource that the customer can depend upon to assure sustainable electricity at their site. that really leads to this label of reliability. We're finding the customers becoming more interested in power quality, kind of avoiding those voltage sags that we see that kind of give a hiccup to our computer and eats away at the lifetime of the computer. The opportunity for heat recovery, or what we call CCHP, combined cooling, heat, and power, to take that heat and rather than exhausting it to the atmosphere, to recover it and use it for a purpose such as air conditioning. Real-time pricing to bring a lower cost of utility bills to the customer. And something that's really intriguing here, I'll just whet your appetite with it, but it's a potential efficiency gains of utilizing DC in the built environment. So let's talk about the fuel cell for a moment. We're pretty familiar with it. It's got three major components: a electrode, we call the anode, in the middle, an electrolyte, and then the cathode. We introduce a fuel to the anode. It reacts and gives off some electrons, and it itself becomes ionized to produce a hydrogen proton. This yellow area or gold area in the middle says, you can go through, I'll let you go through from left to right, but you electrons, you're not allowed. You've got to find another path, which is fortunate for us in engineering because we can select that path to be a load that we want to utilize to drive a light bulb or a vehicle. The electrons then come back a bit spent after giving up that energy for that load and ionize the oxygen from the air that then combines with the proton to produce our product of water. So pretty neat electrochemical process. An example of this is a fuel cell called the proton exchange membrane fuel cell, and its temperature of operation is 90 degrees Celsius. And those two characteristics really differentiate the different types of fuel cells. I'm going to show you 4 different types here because they're part of our future. I want you to appreciate what we are facing. The first one, beyond the proton exchange membrane fuel cell, would be the phosphoric acid fuel cell. It has the same chemistry as the proton exchange membrane fuel cell, but you can see it operates at a higher temperature, about twice as high. And then we have the molten carbonate fuel cell. It has a very different chemistry. In fact, the proton is, or not the proton, but the ion is transported from right to left. And of course, the temperature you can see here is quite a bit higher than the first two that I identified on the chart. The fourth type is solid oxide, which again has yet a different chemistry. You can see that here, and an even higher temperature. So let's just go through this list and look at the applications. Let's start first with the proton exchange membrane fuel cell, and our application will be, of course, the automobile, because that's the type that's selected for the automobile. There it is, the automobile power plant under the hood that was just described by Dr. Thomas, with hydrogen going to the fuel cell for the fuel, air coming from the right for the oxygen, producing a DC current, and an exhaust made up of water and the nitrogen that came from the air. And so an example of this is a General Motors Equinox, but you have the opportunity of seeing the FCHP out here and actually driving it as well. And I think we all know we have Honda, Nissan, Hyundai, and many others evolving this concept. But we're here to talk about distributed generation, which doesn't move. So let's go from the automobile and go to the stationary application. And for that fuel cell, we've got to do something here on the left side. We've got to take a fuel like natural gas and go through a fuel processor in order to extract out the hydrogen. And over here on the right, we can't really use DC today, so we invert that to AC in order to be compatible to the built environment. Where does that come into our future? Well, let's start here with the proton exchange membrane fuel cell. Where that's coming out is right here in your home. This is your garage. May not recognize it, but here's my depiction of a washing machine and dryer, a water heater, and I've left some space right here for your fuel cell. There it is, right there, a 5 kilowatt fuel cell. And lo and behold, we have a manufacturer that's beginning to think about deploying this commercially. That's Plug Power in New York. not quite this size as I had hoped, a little bit bigger. And then there's a company in Oregon, Clear Edge, that is actually commercially deploying this today in California primarily in the Orange County area. So this is beginning to start to take hold in the commercial market. If we look a little bit future out, this morning we're talking about natural gas fueling in the garage. Is the consideration of natural gas fueling not with natural gas but with hydrogen in the garage being converted through the reformation through the fuel cell. If we think a little bit further out than that, we can look at the house of the future, which has photovoltaic on the roof. Well, of course, homes do today. Fuel cells, we're starting to see those coming, but this is a special type of fuel cell. We call this a reversible fuel cell. So you need to think of the day, the sun is out right now, and the photovoltaic is producing electricity for the home, but it's also taking some of that electricity because you're not at home and sending it to the fuel cell, which is taking the water absorbed the night before and electrolyzing it to hydrogen and oxygen. And then at night, that hydrogen and oxygen is used to provide electricity back to the house. But there's a reserve of hydrogen that then can be used to, provide fueling at the home. So this is really an interesting concept. This is not grid connected with electricity, not infrastructure connected with the natural gas. It's a regenerative, renewable, non-fossil fuel, sustainable, if you will, production of electricity, heat, and transportation fuel for the home.